All right, welcome everybody. Today we're going to talk about lesson number 10, which is section 1.9, and it's all about inverse functions. When you hear the word inverse, what comes to mind? Hopefully something about the word opposite comes to mind, because that's exactly what it means to be an inverse. Now, first of all, there is something called an informal inverse. An informal inverse is something that you might be able to just kind of find in your head. Doesn't really require any algebra, and it's really just using the idea of opposites and the idea that an inverse function undoes the operation of the original function. So for example, if you had the f function 4 times x, hopefully you would think that the inverse operation of multiplication would be division, so the inverse function would be x divided by 4. The inverse of adding 9 would be subtracting 9. The inverse of taking the cube root would be cubing. Slightly harder for the last two because you have to do the inverse operations in the right order. If you have the function 3x plus 1, in order to do the inverse operations to get the x by itself, you would first have to subtract 1 and then divide by 3. If you had the function x minus 1 divided by 5 and you were trying to get the x by itself, you would first multiply by 5 and then add 1. So again, these are called informal inverses because it's possible you can just find them with very little work. Something about the notation. So you guys are used to calling functions f of x. From this point forward, we are going to use this notation here to indicate an inverse. It's a little -1 up in the exponent. Now be careful, that is not a negative exponent. So we're not saying that you should move it to the bottom or try to make it positive or anything. We're just saying that it means an inverse. So if you take a look at the pair at the bottom here, if our f function was 4x, then our inverse f function would be x over 4. And again, you're going to use the specific letter for whatever your function is. So the inverse of f would be f to the -1, the inverse of g would be g to the -1, and so on and so forth. Other than just what notation should you use for an inverse, you might have to verify that two functions are inverses. And just so you know, your book uses kind of a bunch of different words. They might say verify that they're inverses. They might say show that they're inverses, or they might say prove that they're inverses, and they all mean the same thing. In order for you to prove that you have a pair of inverses, you have to use composition, which is what we did in the previous lesson, and you have to show that it works both ways. So you have to show first that if you put the inverse into the original, everything cancels out to be just x. You also have to show that if you put the original into the inverse, that also cancels out to just be x. So last lesson, we talked about the fact that what if you found f of g and what if you found g of f? Almost never are those two values going to be the same. The one exception is if you have a pair of inverses. If you have a pair of inverses, not only should the composition be the same both ways, but it has to be x. And the reason why it's x is because that is the identity function. So here's an example already done for you showing that f and g are inverses. And again, your book will sometimes use f and g. Sometimes it will say f and f inverse. If you're trying to show that they're inverses, they're usually going to start by calling them f and g. And then once you're done, you can kind of declare that it's f inverse. So again, you have to always show it both ways. First, you have to show that if you put the g function into the f function, everything's going to cancel to be an x. So if you plug the x plus 7 over 4 in, you then cross out the 4s, cross out the 7s, and you're halfway there. Then to show the other way, you have to take the f function and you have to plug it into the g function. So if you do that, first the 7s are going to cancel, then the 4s are going to cancel, and then you're also going to get x. Only once you have proven it in both directions can you declare that, yes, they are in fact inverses. Notice how the work in each of these looks different. In the first one, you first reduce the 4s and then you reduce the 7s, whereas in the second one, you first reduce the 7s and then reduce the 4s. So order does matter. If you wind up getting the same set of work both ways, it usually means you're proving the same thing twice instead of proving each one once. So just be very careful on that. Let's go ahead and do a slightly different one, so a little harder. Verify that the two functions are inverses. Now, I am telling you to verify that they're inverses, which means I am telling you that they are. And if you just kind of look at them, that should make sense. The opposite of adding one is subtracting one. The opposite of multiplying by 2 is dividing by 2. And the opposite of cubing something is taking the cube root of something. So even just at first glance, the idea that these are opposites should certainly make sense. So you have to prove it both ways, which means we're going to start by putting this entire inverse function in for this x right here. So that's going to be 2 times the cube root of x minus 1 over 2, the whole thing cubed, plus 1. Very important that when you go to do your proving steps, you do them in order. So the first things that are going to cancel is the cube and the cube root. That's going to leave you with 2 times x minus 1 over 2 plus 1. Cancel the 2's. Cancel the 1's. And look at that, you're halfway there. This should actually be your favorite kind of problem on a test or quiz because you know that the answer has to be x. Now, you have to also prove it the other direction. In order to get full credit, you have to be able to prove it both ways. So now we have to take the f function and we have to plug it in to the inverse. So this becomes the cube root of this whole thing, 2x cubed plus 1 minus 1 divided by 2. And again, you have to unwrap your x in a logical order of operation way. So the first things that are going to cancel are the 1's. Then you have the cube root of 2x cubed over 2. Cancel the 2's. And finally, the cube root of x cubed, that cancels out to just be x. So again, the work should look different on the left side compared to the right side. If you wind up with the same work twice, it means you're proving the same thing as opposed to proving two different things. So the nice thing about a question like this is when I ask you to prove that they're inverses, you already know that they are. What if I give you a function and ask you to find the inverse? Now, you'll remember a couple slides ago, if it is an easy problem, it's possible that you could just do it in your head informally without any work. That is always an option, although it's hard for me to give you partial credit if you just write down what you think the inverse is without actually doing the work to get there. So if you're not able to do them in your head, here is a 4-step process that will get you the right answer every time. Step 1, take the f of x that's in the equation and replace it with a y equals. Step 2, interchange all the x's and the y's in the equations. Step 3, resolve the problem for y equals. And last but not least, when you're done, rewrite it as f inverse. Step number 5, you only have to do if I tell you to prove that they're inverses. If I just say find it, then steps 1 through 4 will be enough. So here's an example that's already done for you. Here is my original function, 5 minus 3x over 2. If I want to find the inverse and I want to do it in a methodical way, I'm going to go ahead and complete these 4 steps. So step 1, replace the f of x with a y equals. Step 2, interchange the x's and the y's. Step 3, resolve for y equals. So that means you would cross multiply, you would subtract the 5, you would divide by -3, and you would simplify until you get down to y equals. And then in your final step, replace the y equals with f inverse. So now this is kind of a little bit harder for you to do informally because looking at it, you might not be sure where the negative goes. They actually do look fairly similar. So when doing it informally is not an option, complete these 4 steps and you'll be good to go. Again, prove that they're inverses. You only have to do if I specifically say to or if the homework specifically says to. Let's go ahead and do a few others. So f of x equals 1/2 x minus 3. Again, let's go ahead and follow those 4 steps. So step 1, replace the f of x with a y equals. Step 2, switch the x and y. So x equals 1/2 y minus 3. Step 3, resolve it for y equals. So if I'm going to resolve it for y equals, I'm going to start by adding 3. Then I'm going to multiply by 2. And when I multiply by 2, I have to make sure that I'm multiplying the whole thing, which means I need to use parentheses. Final answer Instead of a y equals, call it f inverse. And whether you distribute it or not, both of those would be perfectly fine. I'm not going to distribute only because I think it's a little bit easier to see the opposite if you leave it as factored. But again, if you multiplied it all the way through, that would be fine as well. Just so you know, the inverse of any linear equation is always going to be another linear equation. That's just how it works. Now we have a cubic function, and always the inverse is going to be a cube root function. So step number 1, replace f of x with y equals. Step 2, swap the x and y. Step 3, resolve it for y equals. So if I resolve it for y equals, I'm going to subtract the 2. Then I'm going to divide by 5. In the final step, to get rid of a cubic, I'm going to take a cube root. So the cube root of this whole thing, x minus 2 over 5. And again, in the final step, replace the y equals with f inverse, and then kind of take a look and make sure that you see everything being an opposite. Again, you only have to prove it if I tell you to. Let's pause and try it and do one more. So here we have f of x equals a cube root. So let's go ahead and follow that 4-step process. Step 1, make it a y equals. Step 2, interchange your x and y. Step 3, resolve it for y equals. So the first thing I have to do to resolve it for y equals is get rid of the cube root, which means I'm going to cube both sides, which means the last thing that I have to do is add 1. And then again, in your final step, you're just going to switch that to be f inverse. So 4-step process that will allow you to find the equation of the inverse every time. Now that you know how to find inverses, and now that you know how to prove inverses, the next thing up is how do you graph a pair of inverses? So it turns out that when you go to graph a pair of inverses, they always have a very specific relationship. They are always, always, always reflections of each other over the line y equals x. The line y equals x, again, that's the identity function. It goes through the origin with a slope of 1. Remember, that's what you have to get when you're proving the composition, so that identity function is showing up again and again. So here I have the lighter gray graph, that's my f function. I have the darker black graph, that's my inverse function. And again, they have to be mirror images, reflections of each other over the line y equals x, which I've gone ahead and dotted there in red. If you knew a point on the inverse and wanted to graph a point on the original, or if you knew a point on the original and wanted to graph a point on the inverse, the way that you do that is for any point that lies on the original, let's say AB, the inverse point, which means flip the x and y, must also lie on the inverse, which in this case would be BA. So the way that you create a pair of graphs that are in fact reflections of each other over the line y equals x is to take any point xy on the original, flip the values, interchange them to become the point yx on the inverse. And again, they will always wind up being reflections over the line y equals x. Here's an example just kind of showing you a few dots. So take, for example, the blue dots. Let's say that the blue dots are the original function. This would be the point 0, 1. If you interchange those x and y values, that's how you get the point 1, 0. They're reflections over the line y equals x. Here you have the point 0, 4. If you invert the x and the y, you get the point 4, 0. So again, these are a pair of inverse points. Here you have the point negative 3, 5. Flip those values, you get the point 5, negative 3. And again, these 2 points are reflections of each other over the line y equals x. So you can do that process for just singular points. And then you can also do it for a whole graph at a time. So here's just a couple more. So over here on the left, let's say that the blue graph is the original cubic. If I were to take points on the blue, interchange the x and the y, I would get the inverse graph in purple, reflections over the line y equals x. Over here on the right, we have 2 lines, which again, the inverse of a linear is always another linear. So the original f in blue, the inverse g in red. Go ahead and dot in that line y equals x, and you'll see they are in fact reflections over that special line. Another example here, just kind of showing you how I actually took each point. So -3, 0 becomes 0, -3, 1, 2, 2, 1, 5, 7, 7, 5, and that is generally always how you find inverses, how you graph them. Everything about inverses means opposite, which means you're always interchanging x and y. Couple more examples, not only to show you examples of inverses, but just kind of to remind you about some different types of pictures. So here, the F graph, notice that this is exponential. Hopefully you remember the purple graph. What's the inverse of an exponential? It's a log graph. So this is kind of just reminding you about the shapes, which again, reflections of each other over the line y equals x. Here we have a cubic function in blue, and then we have a cube root function in black. Again, those are always going to be inverses. Two lines. Finally, because you're always switching x and y to take some original graph and graph its inverse, every time you do that, you are essentially swapping the domain and the range. So always, 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 the domain of the original is going to be the range of the inverse, and the range of the original is going to be the domain of the inverse. So everything about inverses means you're switching the x and the y, the domain and the range. And again, here's another example for you of a pair of inverses, the original there in green and the inverse there in purple. Perhaps you're wondering, will all functions have an inverse? And the answer is no. How do you know? Well, hopefully you remember the vertical line test. Remember, the vertical line test is what tells you if something is a function. The horizontal line test is what tells you whether or not something has an inverse. If you have a function that is lucky enough to pass both of these tests, the vertical and the horizontal, you can go ahead and call that a one-to-one function. So again, that's just a vocab word. Take, for example, these three pictures right here. If I first wanted to confirm that they were functions, I would perform the vertical line test. So if I'm going to perform the vertical line test, let me just get a different color here. About green. If I'm going to do the vertical line test, passes, function, passes, function, passes, function. So yes, they are all functions. In order to test whether or not they pass the horizontal line test, if I draw a horizontal line through the first one, it does not pass. If I draw horizontal lines through the second one, it does pass. And if I draw them through the third one, even though the graph is rising very, very slowly, it is still going to pass the horizontal line test. So do these functions pass the horizontal line test? The first one does not, but the other two do. Are they one-to-one? And again, remember, one-to-one means they passed the vertical line test and the horizontal. So the one in the middle is one-to-one, and the one at the end is one-to-one, and the first one is not. So vertical line test tells you whether something is a function. Horizontal line test tells you whether or not something has an inverse. These are just, again, some examples of some popular pairs of inverses. You have the cube root on the right and the cubic on the left. Here, find the equation of the inverse function below and then graph both. So notice that you're starting with a cubic function. If you want to find the equation of the inverse, don't forget the steps from a few slides ago. Step 1, put a y in for f of x. Step 2, swap the x and y. Step 3, resolve it for y equals. So the first thing I'm going to do is I'm going to add 1. To get rid of the cube, I'm going to take the cube root. So the cube root of x plus 1, that is going to be my inverse function. And again, I could prove that those are inverses if I want. The easiest way to graph the inverse, yes, I could actually plot xy values for the inverse, but an easier way is to take the black graph that's already given, take some points that are on it, and simply flip-flop the xy. So for example, this is the 0.10 on the original. That means that on the inverse has to be the 0.01. Here's the 0.0, -1 on the original, which means the 0.10 has to exist on the inverse. Here's the point 1.5 comma 2, which means the point 2 comma 1.5 has to exist on the inverse. Here, it looks like we have negative 1.5, negative 3, which means negative 3, negative 1.5 is going to exist on the inverse. And then to connect the dots, keep in mind that the graph that you produce has to be a reflection over the line y equals x. So again, let me just go ahead and change my color again. I'm going to connect those green points that exist on the inverse, and the graph that I make has to be a reflection of the original graph. So it looks approximately like this. A little hard to do on my computer with the stylus, but I think it's pretty good actually. So if you already have the original graph, time saver is always just to take points on the original, invert the x and the y, and then that'll give you the graph of the inverse. So again, going back to a couple slides ago, does the function x squared have an inverse? Sadly, it fails the horizontal line test, so the answer is no. We don't just throw it away though and call it a day. What we do instead is take half the graph and ask ourselves the question again. Does it have an inverse now? Well, the answer is yes. So whenever you have a quadratic and you want to find an inverse, you're only allowed to take half of it. Sometimes I will tell you what half to pick, and sometimes you will get to choose. So let's say we're talking about x squared plus 1. Again, on the left, fails the horizontal line test, does not have an inverse. So we're only going to choose half of the quadratic at a time. And in this case, we're going to choose the part that's greater than or equal to 0. We're going to do both. But again, you can either choose for yourself or I will choose for you. So we're going to take x squared plus 1, but we're only going to graph the positive half, which I've gone ahead and shown you there. Here's just kind of another screen here. So we're going to find the equation of the inverse. And even though you're only taking half of it, the process is still the same for finding an inverse. First, you make it a y. Then you switch x and y. So x equals y squared plus 1. Here's the rub whenever you have to do this for a quadratic. Not only are you switching all of the x's and y's in the equation, you're also switching the qualifier at the end. If your original problem says x is greater than or equal to 0, your inverse has to say that y is greater than or equal to 0. And that's going to become important in a minute. So solve for y by subtracting 1. And then how do you get rid of a squared? You take a square root. When you take a square root, you always have to do plus or minus. How do you know which one to pick? Well, go back to this here. You said based on the inverse that y has to be greater than or equal to 0. Well, what's greater than or equal to 0, positive or negative? Obviously the positive. So the square root of x minus 1, that is going to be the equation of the inverse for this equation right here. If I wanted to graph it, again, the easiest way for me to do that is to take a couple points from the original and just invert them. So 0, 1 becomes 1, 0, 1, 2 becomes 2, 1, and then a couple more, and you get part of a square root function, which kind of looks like a scoop. And again, they are reflections of each other over the line, y equals x. Not that it's terribly harder to do this for only half a quadratic, but you do have to remember the qualifiers here, whether or not you're choosing the positive version or the negative version. Maybe you're wondering, are we ever going to choose the negative version? And yeah, we definitely are. So now back to the original problem, x squared plus 1. This time, we're going to choose the negative half, which is true for x is less than or equal to 0. So again, here it is, just kind of on its own screen. And the original process still the same, make it a y equals, switch the x and y. Don't forget the qualifier, so y has to be less than or equal to 0, because remember, everything has to change about the x and the y. You're going to subtract the 1. You're going to take a square root. You're still going to have to say plus or minus, but now, because of the fact that you want y to be less than or equal to 0, you're going to choose the negative version of the square root and be the inverse. How would you graph that? Well, again, take some points from the original and flip them. So 0, 1 becomes 1, 0. -1, 2 becomes 2, -1. -2, 5 becomes 5, -2. And you're going to have a scoop that looks like this. That's a negative square root. And again, they have to be reflections of each other over the line y equals x. Last but not least, there are a couple of really cool algebraic problems we can do with inverses and composition. And here you just have to pay very, very, very close attention to the order. So notice here in this example, I give you an f function, which is x over 4. I give you a g function, which is x cubed. I am asking you to find the composition, remember the open circle means composition, of the inverse of g with the inverse of f of 27. So there's kind of a lot going on here. So I'm going to start by finding each of the inverses. And I kind of picked easy ones on purpose that you could hopefully do with very little work. So the inverse of f, the inverse of x divided by 4 is 4x. The inverse of x cubed is the cube root of x. So there's my inverse f and there's my inverse g. And I want to take my inverse g and I want to put it into my inverse f, but I want to do that for the number 27. So I'm going to start by plugging 27 into the inverse of g. That becomes the cube root of 27, which becomes 3. Then I want to plug that 3 into the inverse of f. 4 times 3 gives me a final answer of 12. So I know that work isn't kind of the nicest. You could probably, make it a little bit more methodical, but when you're asked to do problems like this, you just want to be very, very careful to follow the order. So find the inverse of g, find the inverse of f, put the 27 into g inverse, put whatever that answer is into f inverse. Here's one that's a little bit different. So again, I give you an f and a g, both of which are very simple. And here I'm just asking you to compose the inverses, so no numbers. So start by finding the inverse of f, which the inverse of x plus 4, hopefully should very easily be x minus 4. If at any time you need to complete the 4-step process, feel free. If not, then in your head is fine. So the opposite of 2x minus 5, you would first have to add 5 and then divide by 2. So there's my f and there's my g. Remember, you're working from the inside out, which says you're going to put g inverse into f inverse. So that means you're going to replace the x with x plus 5 over 2. Then you're going to subtract 4. The way that you would do that is by finding a common denominator. So a common denominator would be 2. That means this is x plus 5 minus 8. That's going to give you x minus 3 over 2. And remember what I told you yesterday, generally speaking, if you put numbers in, you get numbers out. That was the previous example. If you put variables in, you get variables out, and that's what happened here. One last problem, it's the same f and the same g, but notice now instead of doing the inverse of g composed with the inverse of f, we're now going to put the regular g into the regular f and then take the inverse of the whole thing. So taking the inverse is actually the last thing that's going to happen because of the fact that everything is inside of the parentheses. So f circle g, that means you're going to put the g function into the f function. So this is going to become 2x minus 5 plus 4. That becomes 2x minus 1. Then you are going to take the inverse of that. Again, feel free to set up a process and do the work if you need to. Otherwise, the inverse of 2x minus 1 would be to add the 1 and then divide by 2. So I kind of lost, my equal signs and et cetera. So don't worry too much about that for more complicated problems such as this. You just want to make sure that you can kind of get down to the final answer. And that's really all we're looking for. And for problems like this, more than anything else, order matters. So that's everything you need to complete homework 10, which is in section 1.9, and it's the following problems. Go ahead and write those down. And remember, feel free to review the lesson as many times as you want. Thanks very much for tuning in, and we will catch you next time.